In a previous lecture, we reviewed the steps and the calculations involved in performing an analysis of variance, or ANOVA. In this lecture, we continue our review by performing an ANOVA on data in the context of an example. Here's an outline of what we'll be looking at in this video. We'll first provide a description of the experiment that we're going to be analyzing. We'll perform the ANOVA using the calculations that we reviewed in that previous lecture video. Along with that, we're going to construct two confidence interval estimates of the model error variance sigma squared. The first will be based on the chi-square distribution, and the second will be based on the normal distribution. We'll also perform the ANOVA using SAS, both PROC GLM and PROC mixed. We will obtain a confidence interval estimate of the model error variance based on the chi-square distribution by programming the calculations in a data step and also directly from SAS PROC mixed. And then finally, we'll determine whether the confidence intervals for the model error variance can be relied upon by checking the plausibility of the model assumptions, as well as the shape of the chi-square distribution of the point estimator of the model error variance. So let's get to it. So this is example 3.1, and it's a comparison of 4 rice varieties. Here is a description of the experiment. An experiment was conducted to compare the yields of 4 varieties of rice of particular interest to a researcher. Each of 16 plots on a test farm, where soil fertility was homogeneous, was treated alike with respect to water and fertilizer. Each of the 4 varieties of rice was randomly assigned to 4 plots on the farm. The yield, scaled to pounds per acre, was recorded for each plot. Because each variety was assigned to 4 plots completely at random, this experiment has a completely randomized design. Let's look at the raw data for this experiment as well as some basic summary statistics. Here we have the tabular organization of the data. You see we've got 4 columns in the body of the table, 1 column for each of the 4 rice varieties. And in the body of the table, we have the actual data itself. Then in the last 4 summary rows, we have a number of summary statistics. So we have the number of reps per sample. You can see we have equal replication. We have 4 reps per sample for a total of 16 observations. The next row gives the sum of the yields for each of the varieties. The next row gives the mean yield for each of the varieties. And then finally, in the last row, we have the sum of squared yields for each of the varieties. And then in the far right-hand column, we have some summary statistics for the overall data set. So we have the overall total number of observations. We have the overall sum of the yields for the various observations. We have the overall mean, which is equal to the sum divided by the number of reps. And then finally, we have the total sum of squares, which is the sum of the individual sample sums of squares. Let's now fill out the degrees of freedom column in the ANOVA table. And so we have 4 treatments, and so the number of degrees of freedom associated with treatments is 4 minus 1, or 3. We have 16 observations total, and so the total number of degrees of freedom is 16 minus 1, or 15. And then to get the degrees of freedom for error, we subtract the degrees of freedom for treatments from the total degrees of freedom, so 15 minus 3, and that gives us 12 degrees of freedom for error. Next, we will calculate the sums of squares for the ANOVA. And so we're going to be using information from this summary table. Now, the first thing that we'll calculate is what's called the correction term. You will recall that when we're calculating a corrected sum of squares, we can do that a little bit more easily using a computational formula, which is the difference between the appropriate uncorrected sum of squares and this correction term. And so the correction term is equal to the square of the sum of all the observations in the data set, so y dot dot squared divided by the total sample size, or n. And so the correction term for this data set, for this analysis, is 15,743,040.0625. Now, to get the total corrected sum of squares, we calculate the uncorrected sums of squares for the total, which is that first term, and then we subtract from that the correction term, c, and so we get, you can see here, 139,806.9375. To get the treatment sum of squares, we calculate the appropriate uncorrected sum of squares for the treatments, which is that first term, and then we subtract from it the correction term. And so you can see here that the treatment sum of squares is 89,931.1875. Once we have the total corrected sum of squares and the treatment sum of squares, we get the sum of squares for error by subtraction. So we subtract the treatment sum of squares from the total corrected sum of squares. And we see here that the sum of squares for error is 49,875.75. So now we have everything we need to fill in the sums of squares column for the ANOVA table. And so again, the sum of squares for treatment was 89,931.1875. The total sum of squares was 139,806.9375. And again, we get the sum of squares for error by subtraction. And so we get 49,875.75. Now we calculate the mean squares for the ANOVA. To get a particular mean square, we divide the appropriate sum of squares by its corresponding degrees of freedom. And so to get the mean squares for treatment, we divide the sum of squares for treatments by its degrees of freedom, which is t minus 1 or 3. And so we see here that the mean square for treatments is 29,977.0625. The mean square error is obtained by dividing the sum of squares for error by its degrees of freedom, which again is n minus t, or 12. And so we get 4156.3125 for the mean square error. Now we can fill out the mean squares column in the ANOVA table. And so we have mean squares for treatments of 29,977.0625. And the mean squares for error is 4156.3125. Finally, we can calculate the F statistic for the analysis of variance. The F statistic is the ratio of the mean squares for treatments divided by the mean squares for error. And so you see here that we get 7.2124 approximately. And if we round that to 2 decimal places, that would be 7.21. And so we see here that when we have the ANOVA table in front of us, we can very easily calculate the F statistic by taking the ratio of the mean squares for treatments by the mean square for error, and that gives us 7.21. One thing I want to point out is that the ANOVA table is not only a convenient way of organizing and presenting the information from the ANOVA, but it also facilitates the calculation of the mean squares and the F statistic once we have the degrees of freedom column filled out and the sum of squares column filled out. So once we have those first two columns, we can get the mean squares by dividing the sum of squares in that row by the degrees of freedom in that row. And once we have the mean squares column, at least for this simple type of model, we see that we get the F statistic by taking the ratio of 29,977.0625 and 4156.3125. So again, not only is this a convenient way to organize and present the results, but it's also a way to help us remember how to do some of these calculations. Now here is the same kind of analysis. I've done it in the context of a spreadsheet just to verify the work that we've done by hand. And you can see here that at the very bottom of the screen, or very bottom of the slide, we have an F statistic of 7.2124, and that corresponds to what we got when we did it by hand. And the p-value, which we did not have when we did this by hand, but it's very easy to get this using software such as a spreadsheet or a statistical program. We see that the p-value for this test is 0.005034. Now it comes time to interpret the results. So in this case, the null hypothesis being tested is that mu1, mu2, mu3, and mu4 are all equal. That is, there are no differences among the four population or treatment means. The alternative hypothesis is that differences do exist among the four population or variety means. So at least one of the mu's is different than the rest. And again, mu sub I represents the mean yield for rice variety I going from 1 to 4. The test statistic was equal to 7.21. The critical point for the test, since we're doing this at the 0.05 level of significance, that critical point is the upper fifth percentage point of the F distribution with 3 numerator degrees of freedom and 12 denominator degrees of freedom. That critical point is 3.49. We see that the test statistic, 7.21, is greater than the critical point, 3.49. The p-value, which is 0.005034, is less than or equal to the significance level that we're using for the test, 0.05. And so we see that there is sufficient evidence at the 0.05 level of significance to reject the null hypothesis and conclude that differences exist among the mean yields of the four rice varieties. Now we're going to construct two confidence interval estimates of the error variance sigma squared. The first interval is going to be based on the chi-square distribution, which is the actual distribution of our point estimator of sigma squared. And so a 95% confidence interval estimate of sigma squared, the variance of the model error term, based on the chi-square distribution, is given by this expression. So the lower end point is equal to the product of the degrees of freedom and the point estimate of sigma squared divided by the upper alpha over 2 percentage point of the chi-square distribution, with degrees of freedom equal to the number of error degrees of freedom in the ANOVA table. The upper end point is the ratio where in the numerator we have the degrees of freedom for error times the point estimate of sigma squared divided by the upper 1 minus alpha over 2 percentage point of that same chi-square distribution. We have 12 degrees of freedom for error. The point estimate of sigma squared, which is the MSE from the ANOVA table, is 4156.3125. Since we're constructing a 95% confidence interval estimate of sigma squared, alpha is 0.05, and so alpha over 2 is 0.025. The upper 2.5 percentage point of the chi-square distribution with 12 degrees of freedom is 23.337, And the upper 97.5th percentage point of that chi-square distribution is 4.401. And so when we do the calculations, we get a 95% confidence interval estimate of sigma squared. And let me just say here, it's a nominal 95% confidence interval estimate of sigma squared that ranges from 2137.1963 up to 11325.1022. Now, note the asymmetry of this confidence interval estimate about the point estimate sigma hat squared, which is 4156.3125. The length of the portion of the interval above the point estimate is given by this difference, so the upper end point minus the point estimate, 11325.1022 minus 4156.3125. And so the length of the portion of the interval above the point estimate is 7168.7897. On the other hand, the length of the portion of the interval below the point estimate is given by 4156.3125, the point estimate, minus the lower end point of that interval, 2137.1963. And so the length of that portion of the interval below the point estimate is 2019.1162. And so we can see here that the portion of the interval above the point estimate is 3.55 times longer than the portion of the interval below the point estimate. And as you'll recall from our previous video where we talked about this interval, this is actually a desirable feature because the sampling distribution of sigma hat squared is a skewed distribution. It's skewed to the right. And so having an interval that is asymmetric like this, where the portion above the point estimate is longer than the portion below the estimate, is entirely appropriate. Now let's construct a confidence interval for sigma squared based on the normal distribution. An approximate 95% confidence interval estimate of the variance of the model error term, sigma squared, based on the normal distribution, is given by the following expression. So the lower end point of this interval is sigma hat squared times the quantity 1 minus z sub 0.025 times the square root of 2 over 12. And the upper end point is sigma hat squared, the point estimate, times the quantity 1 plus z sub 0.025 times the square root of 2 over 12. So when we carry out those calculations, we get the approximate 95% confidence interval estimate of sigma squared that ranges from 830.5699 up to 7482.0551. Now note that this confidence interval, by virtue of its construction, is symmetric about the point estimate sigma hat squared equal to 4156.3125. The lengths of the portions of the interval both above and below the point estimate are equal, and they are equal to 3325.7426. Now, as you recall from our previous lecture where we talked about this particular interval, this symmetry of the interval is really not a desirable feature because the sampling distribution of sigma hat squared has some skewness to it. And so this kind of an interval can be expected to be accurate only if there's not much skewness in the sampling distribution of sigma hat squared. Now let's analyze the data using SAS. The first thing we need to do is create a data set containing our data. And so here is the data step to do that. We'll first use PROC GLM to analyze this data and perform the analysis of variance. And so here is the SAS code to perform the ANOVA using PROC GLM. Now we've got several statements in here that you may not have seen before. We're going to focus on the first few within the PROC GLM statement. So we invoke PROC GLM, and then we tell it the data set that contains the data we're going to be analyzing. And I'm also telling it to print out some diagnostic plots as well as the residual plots. The class statement, class variety, tells PROC GLM that the variety variable contains the values for the different varieties. It's identifying the classification variable to PROC GLM. We then specify the model that we're fitting. It's an ANOVA model where yield is the response variable, and then the variety is the explanatory variable. I have an output statement where I'm going to output residuals from this model to an output data set called out1. And then I also have an LS mean statement and a mean statement. We'll talk about those a little bit later. And so here is the ANOVA table produced by PROC GLM. And so you can see here that we have 3 model or 3 treatment degrees of freedom. We have 15 total degrees of freedom, and we have 12 degrees of freedom for error. If you compare the various sums of squares with what we got before, and the mean squares, as well as the F value, 7.21, we see that these values agree with those we obtained when we did the calculations by hand. In addition, the p-value that is returned by PROC GLM is equal to the p-value that we obtained from the spreadsheet software. Now let's construct a 95% confidence interval for sigma squared based on the chi-square distribution. And so now that we have the results from the ANOVA, I'm going to take some of those results and perform another data step where I'm creating a data set called confidence limits. And you can see here that I'm creating a variable for alpha because we want to construct a 95% confidence interval. So 1 minus alpha times 100% would be 95%. I'm hand entering the number of error degrees of freedom into this data step. I'm calling that variable error degrees of freedom. I've also copied the value of sigma hat squared, the estimate of sigma squared, from the ANOVA table. All right, that is the estimate of the error variance, and it's equal to 4156.3125. That is the MSE, the mean squared error, from the ANOVA table. And then I do the calculations to get the appropriate chi-square values that we use to divide in that formula. And then I calculate the lower and upper confidence limits for this confidence interval. And so you can see here that we get lower and upper confidence limits of 2137.23 and 11325.65, which are the values that we got when we constructed this interval by hand. Next, we're going to use PROC Mixed to perform this analysis of variance. And we're going to do this because it's easier to get the confidence limits for the confidence interval for sigma squared directly using PROC Mixed. And so here is the SAS code to perform the ANOVA using PROC Mixed. So I invoke the procedure with PROC Mixed, and then I specify the data set that contains the data equal rice. I want the output produced by PROC Mixed to look like the output from PROC GLM and also to look like what we constructed by hand. And so I'm going to issue the method equal type 3 option. Now let me just say that if we don't do that, it's still going to do an appropriate and correct analysis. It's just going to use REML estimation, residual maximum likelihood, as opposed to doing the types of calculations that we did by hand and the calculations that PROC GLM does. And it will, because of that, present the results in a little different format. But I want to get the output from PROC mixed in a manner that looks, or in a format that looks like what we got from PROC GLM. And so this is the way to do that. I then issue the COVE test and CL options. We'll talk about those in a minute. And then I have the class statement to identify to PROC mixed the classification variable, which again is variety. And then I specify the model in the same way I did PROC GLM, because this is just a fixed effects model. So model yield equal variety. And so the method equal type 3 option instructs PROC mixed to produce this table that we see here, the type 3 analysis of variance. This is the same type of analysis that PROC GLM does. And so you can see here that we have a column in this table for degrees of freedom, as we did when we obtained the results from PROC GLM. So we have 3 treatment degrees of freedom and 12 error degrees of freedom. We have a column for the sums of squares, and you can compare those values to what we got from PROC GLM, as well as the values that we got when we calculated these things by hand. Next, we have a column for the mean squares, and again, compare those with the values we got by hand and also the values we got from PROC GLM. Now, note also that we have an additional column in this table. We have a column that tells us the number of error degrees of freedom for variety. And so we see that that is 12, and that corresponds to the number of degrees of freedom for error that we see in that first column. Next, we have a column for the F statistic, 7.21, which is what we got up before. And then finally, it gives us the p-value in the last column, 0.0050, which again is what we got using the spreadsheet as well as PROC GLM. Now, what is being tested by this F statistic? What is being tested by that p-value? Well, to answer that question, we need to look at the expected mean square column. And so when we look at the entries in that column, what we can see is that the expected mean square for treatments, that is variety, is equal to the sum of 2 components: the variance of the error terms and a quadratic form involving variety. And that quadratic form is going to be 0 if and only if the Rice variety means are all equal. So the expected mean square for treatments will be equal to the expected mean square for error, which, by the way, is just the variance of the error term, if and only if the Rice variety means are equal. And so based on this, we know that the hypotheses being tested by that F statistic and by that p-value are as follows. The null hypothesis is that the mean yield of the 4 Rice varieties, they're all the same, against the alternative hypothesis that differences exist among the 4 Rice varieties in terms of their mean yields. Now let's look at the output produced by the COVE test and CL options on PROC mixed statement. And so the COVE test option is going to instruct PROC mixed to include some additional columns in the covariance parameter estimates table. Typically, it's going to give you a table with the estimate and the standard error, but when we issue the COVE test option, it's also going to provide a p-value. All right, and what this is testing is the null hypothesis that the variance of the error terms is equal to 0. We see the p-value of this test is 0.0072, and so based on that, we would conclude that the error variance is not 0, it's something greater than 0. However, this test is really not of interest here. This kind of test would be of interest only if we've got say, a mixed model or a random effects model where we've got more random effects. Now the CL option instructs PROC mixed to include a 95% confidence interval estimate for the error term, variance. And so we see here that the lower endpoint is 2137.23 and the upper endpoint is 11326. Those are the same values that we obtained when we constructed the interval based on the chi-square distribution. And so we can see here that at least when calculating a confidence interval for the error variance, PROC mixed is using that same type of approach. It's using a confidence interval estimation method based on the chi-square distribution. Now let's compare and evaluate the two types of confidence intervals that we've constructed. A 95% confidence interval estimate of sigma squared based on the chi-square distribution ranged from 2137.1963 up to 11325.1022. Now again, that is an asymmetric interval, with the portion of the interval above the point estimate being 3.55 times longer than the portion of the interval below the point estimator. And that's a good thing. The width of the interval is 9187.9059. The 95% confidence interval estimate of sigma squared based on the normal distribution ranged from 830.5699 up to 7482.0551. This was a symmetric interval in the sense that the length of the portion of the interval above the point estimator is equal to the length of the portion of the interval below the point estimator. And that is not necessarily a good thing because the sampling distribution of sigma hat squared is skewed to the right. The width of this interval is 6651.4852. And so when we compare the two widths, we see that the interval based on the normal distribution is much narrower. It's much more precise than the interval based on the chi-square distribution. Now we like our confidence intervals to be precise, and if we can choose between two or more confidence intervals, everything else being equal, we would like to choose the one that is the most precise. But the question here is everything else equal? And in particular, are the confidence levels, the true confidence levels of these two confidence intervals actually the same? So we see that these two intervals are quite different. The question is, are either of these intervals trustworthy? Can we rely on either of them? Now, each has a nominal confidence level of 95%. But can we have confidence that the true confidence level of either interval is in fact 95% or at least close to it? You see, here's the issue. Even though we might construct what we might call a 95% confidence interval for a parameter, if the sampling distribution, the true sampling distribution of the point estimator of that parameter is not well approximated by the distribution that we're using to come up with the confidence interval, then the true confidence level, the true coverage probability may not be 95%. It may be 90% or 80% or even worse. It might be only 70%. And so we need to make sure that we distinguish between what is called the nominal confidence level. We say we're constructing a 95% interval, but that's always an approximation because every procedure that we use is an approximation. So we need to distinguish between the nominal confidence level and the true confidence level. The true confidence level really is something that we'll never know, all right? And so we need to check whether model assumptions appear to be met, and we need to look at other things in order to see how confident we can be that the true confidence level is at least close to the nominal confidence level. And so with that in mind, we need to look at some questions. First, are any of the model assumptions violated And the second, how well is the chi-square distribution with 12 degrees of freedom approximated by a normal distribution? And the reason we need to look at that second question is because the normal distribution is the distribution that we used to come up with that second confidence interval. The chi-square distribution with 12 degrees of freedom is the true sampling distribution of our point estimator, sigma hat squared, at least if the model assumptions are met. Let's first check for violations of the model assumptions. We'll start off by checking for violations of the normality assumption. And so here I have PROC univariate, and I'm going to be analyzing data from the data set called OUT1, which you'll recall is the data set that I output the residuals from our model to. The normal test option on the invocation of PROC univariate tells PROC univariate to perform a formal test of the null hypothesis that, in this case, the residuals come from a normal distribution. In addition, the histogram statement will produce a histogram of the variables in the var statement, which in this case is the variable residuals. That contains the model residuals. And so the histogram statement is going to create a histogram of the model residuals. The normal option to the histogram statement is going to superimpose a normal curve with the same mean and variance as the residuals over the histogram of the residuals so that we can compare the shape of the histogram of the residuals to a corresponding normal distribution. And finally, the PP plot statement is going to produce a probability plot of the residuals versus corresponding values from the normal distribution with the same mean and variance as the residuals. And so here is the histogram of the residuals produced by PROC univariate. From this, we can see visually that the histogram of the residuals shows some left skewness in the distribution of the residuals. We can see here numerically that the skewness coefficient is indeed negative. The skewness coefficient for the model residuals being negative 0.9234. Next, we have the PP plot for the residuals. If the model error terms are indeed normally distributed, then the residuals should fall fairly closely to that equiangular line. Now we see that there is some deviation of the residuals from the line, providing some visual evidence against the assumption that the model error terms are normally distributed. However, with only 16 residuals, some deviation from the line would be expected. This is because we are essentially comparing the empirical distribution of the residuals to the corresponding normal distribution with the same mean and variance as the residuals. And with only 16 observations in that residual data set, the empirical distribution is going to be fairly choppy. And so that's why we would expect to see points not fall perfectly on this line. And so in my view, this plot really does not provide strong evidence against the normality assumption. So here is the output from PROC univariate where we asked it to perform the formal test of the normality of the residuals. And so the question we have here is that, is it reasonable to assume that the model error terms are normally distributed? Well, here are the p-values for that test, and you can see here that PROC univariate provides 4 different tests to test this hypothesis. Now, I typically like to use the Shapiro-Wilk test when I'm doing these kinds of things, but there are others as well. The Kolmogorov-Smirnov test, the Kramer-von Mises test, and the Anderson-Darling test. And you can see here that if we were going to use the Shapiro-Wilk test, the p-value testing the null hypothesis that the error terms are normally distributed is 0.0810. And so based on that, we would not reject the null hypothesis that the error terms are normally distributed, at least not at the 0.05 level of significance. If we were to use the Kolmogorov-Smirnov test, we would reach the same conclusion, although that p-value is approaching significance. The same thing for the Anderson-Darling test. Again, that p-value is slightly larger than 0.05, and so if we were using a 0.05 level, we would not reject. If we were using the Kramer-von Mises test, then the p-value is 0.0438. That is less than or equal to 0.05, and so one could choose to reject the null hypothesis of normality of the error terms based on that. But keep in mind that that p-value, even though it is less than or equal to 0.05, so there is some evidence based on that test statistic that the error terms are not normally distributed. It's not super strong. And so, in conclusion, I would say that there is some evidence that the model error terms are not normally distributed, but again, the evidence is not really strong. This slide just puts all of these results on one page so that we can see them at a glance. Next, let's check for violations of the constant variance assumption. Let's take another look at our PROC GLM code. See at the top I've got plots equal to, and so I've requested some diagnostic plots as well as plots of the residuals. I've also included the mean statement there at the bottom, and with the mean statement I've included the HOV test option. The HOV test option of the mean statement in PROC GLM forms a test of the homogeneity of variance assumption. Here's a set of side-by-side box plots, one for each of the four varieties, and these are box plots of the yield. Now, for our current purposes, what we want to focus on is comparing the variation across the four samples. In these box plots, we can see differences in the range, that is the maximum minus the minimum, of the, and this says residuals here, but it's actually of the yields, from one treatment group to the next, which visually corresponds to the distance between the tips of the whiskers for the box. Now, this is not too surprising because the range is based on only two data points in a sample. In fact, the most extreme values, the maximum value and the minimum value. And because of that, as a measure of variation, the range is itself quite variable. In other words, it's kind of unreliable. We also see variation in the lengths of the boxes themselves, that is the interquartile range, although these do not differ as much. Again, that is not too surprising because the interquartile range is based on the first and third quartiles, and as a measure of variation, the IQR is less variable than the range is. And so we would expect to see less variability from one sample to another in terms of the IQR if in fact the variability is the same from one treatment group to another. So to summarize, there is some visual evidence in these box plots that the variability may differ across treatment groups, although to be honest with you, it's hard to determine visually whether these observed differences are significant or just due to chance. Next, we will look at a formal test of the constant variance assumption. Here is the output produced by the HOV test option on the mean statement. And so we see here that we have, in the far right-hand side, we have a p-value. This looks like the ANOVA table from the output from PROC GLM. In fact, we see that the degrees of freedom are the same. It's got the same columns: degrees of freedom, sums of squares, mean square, F, and the p-value. But the question is, what is that p-value testing? What is that F statistic testing? Well, this analysis is testing the following hypotheses. The null hypothesis is that the error variance is the same under all treatments, or for all 4 varieties. The alternative hypothesis is that the error variance differs from one treatment to another. Now the p-value is 0.4886. It's quite large. And so since the p-value is not less than or equal to 0.05, the constant variance assumption is not unreasonable at the 0.05 level of significance. We would not reject the assumption or the hypothesis that the error variances are the same across the 4 varieties. Next, let's look at what the chi-square distribution with 12 degrees of freedom looks like. And so this is the PDF, the probability density function, of the chi-square distribution with 12 degrees of freedom. And you'll recall that 12 degrees of freedom is the number of degrees of freedom for error in our ANOVA table. And so if the model assumptions are correct, then this is the sampling distribution of the MSE. This is the sampling distribution of sigma hat squared. And so visually we can see that this distribution has some right skewness to it. It's not perfectly symmetric like the normal distribution is. In fact, numerically, the skewness coefficient for this distribution is approximately 0.81. Now, comparing that to the skewness of a normal distribution, which is 0, we see that this does have more positive, or it's got positive skewness. It's got more skewness than the normal does. All right, so this quantifies what we're seeing in the graph. In addition, the kurtosis of this chi-square distribution is 4, which is 33% greater than the kurtosis of a normal distribution. And just as an aside, the kurtosis of every normal distribution is 3. And so based on these results, the sampling distribution of sigma hat squared, which is the chi-square distribution with 12 degrees of freedom, would not appear to be well approximated by a symmetric distribution like the normal distribution. So which of the confidence intervals for the error variance can we trust? Can we trust either of them? So with regard to the confidence interval based on the chi-square distribution, these confidence limits are accurate and the confidence levels are exact as long as the assumptions about the model error terms are true. If the assumptions are not true, then the confidence limits and confidence levels will be approximate at best. The more closely the assumptions are to being met, the more accurate the confidence limits and confidence levels will be. Now, in this situation, the constant variance assumption is perfectly reasonable. There was no evidence, really numerically, in that test that the variances differed across the 4 varieties. Now, regarding the normality assumption, even though there was some negative skewness in the residuals, it really was not enough to be significant in 3 of the 4 tests that we looked at. And so I would say that the normality assumption is reasonable at the 0.05 level of significance. And so based on the criterion in the first bullet point and the results that we're looking at here in the second and third bullet points, I'd say that we can conclude that the confidence limits are pretty accurate and the true confidence level is close to the nominal level of 95% for the confidence interval based on the chi-square distribution. Next, regarding the confidence interval that is based on the normal distribution, in addition to the requirements on the previous slide, the accuracy of the endpoints and the confidence level for this confidence interval depends on how well the true sampling distribution of sigma hat squared can be approximated by a normal distribution. Even if we assume that the requirements on the previous slide are met, because the degrees of freedom associated with the point estimator sigma hat squared is really not that large, only 12, as we have seen, the sampling distribution of sigma hat squared still has a fair amount of right skewness in it. In addition, the kurtosis of the sampling distribution of sigma hat squared is 33% larger than the kurtosis of the approximating normal distribution. And so because of these things, the confidence interval based on the normal distribution really cannot be expected to provide accurate endpoints, nor can the confidence level be expected to be very close to the nominal level of 95%. And this is especially true if you recall that the confidence interval that we obtained using the normal distribution was so much shorter than the confidence interval we obtained using the chi-square distribution. And so as a result, in this particular situation, we should not rely on the confidence interval that is based on the normal distribution. So let's summarize what we've done. We described the experiment, a comparison of the yields of 4 rice varieties. We performed the ANOVA to do this by hand using the procedure we described in a previous lecture video. We constructed 2 confidence interval estimates of the model error variance, one based on a chi-square distribution and one based on a normal distribution. We also performed the analysis using SAS, both PROC GLM as well as PROC mixed. And using SAS, we obtained a confidence interval estimate of the model error variance based on the chi-square distribution by first programming the calculations in a data statement, but we were also able to get the confidence interval directly from SAS PROC mixed. And finally, we concluded that the asymmetric interval provided by the chi-square distribution should be reliable, but the symmetric interval based on the normal distribution should not be relied upon in this particular situation. So that's what I wanted to show you in this lecture video. I'll see you in the next video.